Alrighty, well, chapter 9 is the first of our two chapters on chemical bonding. So we're going to start with Lewis theory, which involves pretty much bonding of valence electrons. Let's just write that here, just so we know what we're talking about. So we're forming compounds. Okay? The chemical bond differs by the type of compound that we've formed here. So the first two types of bonds in this little table here are types that we've seen before. Okay? An ionic bond is what happens between a metal and a nonmetal. It happens because electrons are transferred. Okay? We're going to go into that in a little more detail on just the next page. Okay? But it's ionic because we've seen before that metals tend to form positive ions. Nonmetals tend to form negative ions. It ends up being the attraction of those positive and negative ions that holds an ionic compound together. Okay? In a covalent bond, that is between a nonmetal and another nonmetal. And instead of transferring electrons, valence electrons are shared. And we'll talk about exactly why and how that happens. But covalent bonds, let's also write molecular compounds right here for molecular compounds. A molecular compound has covalent bonds within the molecules of that compound, but then each molecule exists as a unit. So think of something like water, where you have hydrogen, oxygen, hydrogen. There are covalent bonds that hold the atoms together inside of that molecule, but then each water molecule acts as a separate unit from the other water molecules around it. Okay? If you take a look at these little pictures here, you start to get a little bit of a picture in your head of what we're talking about, and we're going to go into more detail on this. But in this nice little picture of sodium chloride, table salt, NaCl solid, ionic bonding happens between oppositely charged ions. They all end up stacking together in what's called a lattice. That's the structure formed by oppositely charged ions all stacked together. And you'll notice there are sort of no individual subunits there. It's just kind of alternating plus minus, okay, and stacked up in 3 dimensions throughout the entire structure of that substance. Okay? We're going to talk about why that is. Compare that with a molecular compound. Okay? Water has covalent bonding inside of those molecules. Okay? I'm going to draw an arrow right inside one of those molecules. In fact, why don't you just draw a water molecule like that? The covalent bonding is what holds one atom close to the other atom inside of a molecule. Okay? But then you have that individual grouping of atoms that makes a molecule, but then you've got a totally separate water molecule next to it. Okay? So, completely different idea between molecular and ionic compounds. That's a key difference in introductory and general chemistry that you really need to be aware of. How does a molecular compound look different from an ionic compound at the atomic level? Okay? Ionic compounds have ions alternating, all totally stacked up like that. Really the best we can talk about is what ratio of those ions. That's why we simplify ratios in ionic compounds. We just call it NaCl. Okay? Just because the 1-to-1 ratio is the simplified ratio of all of the atoms involved in that. Whereas in molecular compounds, we're talking about literally the number of atoms contained within one of those molecules, not simplified. Okay? So we can have H2O2 molecules and C12H22, molecules. You can have it's whatever atoms are contained within that actual grouping, and then there's another grouping just like that next to it. So when we have ice, we have all these water molecules. The molecules are the things that get stacked up. Okay? but each of those molecules themselves are individual units. So make sure you have that little picture in your head where you can keep that difference apart. Metallic bonding happens in pure metals. Let's write that. And metals of different elements, I guess they sort of do this, but they don't necessarily form compounds. But we'll think specifically of pure metals. So if we have a sample of aluminum, or a sample of sodium, or a sample of iron, or something like that that's a neutral, pure metal, what happens is the atoms all stack up, but then the electrons are pooled. It says an electron, whoops, over here it says an electron C. Those electrons are shared between, let's say, valence electrons, VE, shared between all atoms. So unlike all these other ones, the valence electrons are not localized onto a particular atom. So the valence electrons are free to move throughout the entire structure of it. And that gives metals particular properties. What do we say that metals can do with electricity? They conduct electricity, and electricity is just the movement of electrons through a substance that allows the electrons to flow. So it's that behavior, that sea of shared electrons that's free to move throughout the entire substance that gives metals many of their properties. Also, the fact that metals are malleable and ductile, we talked about those properties before, comes from the fact that there's no real direction to the metallic bonding. Since it's just kind of general attraction between the atoms and those shared electrons, we can smash metals down into thinner layers, and those layers just kind of reconfigure, or we can stretch it, or we can squish it, and stuff like that. Whereas compared to ionic compounds, that lattice has to be in a very particular arrangement because opposite ions are attracted to each other. And if we smash that, it'll probably just break. Okay? In fact, same thing with the molecular solid. Those molecules kind of need to arrange themselves in very particular directions, and we'll talk about that. But that's another example of where microscopic properties of atoms and molecules directly influence the macroscopic, the overall properties of the substances. Okay? So all that stuff has significance and has purpose to the overall properties that we can talk about. So let's talk about Coulomb's law. We've alluded to this many times already, whether you know it or not. Okay? Coulomb's law just basically describes the attraction of opposite charges and the repulsion of same charges, of similar charges. Okay? But it does so in a way that you can actually predict the energy change associated with particular charges. So E is just energy, right? That's just the energy of a particular interaction. Okay? You could think of it, I suppose, as potential energy. There's a constant there. Q1 and Q2 are the two charges. Okay? And charges have a sign and a magnitude. Okay. Magnitude is just kind of amount. So that means we could have like 1 plus or 2 plus or 3 plus, right? 2 minus, 3 minus, 1 minus, whatever. Okay. So we're comparing what happens with two charges, and down below, divide by r, that's just the radius, right? The distance, atomic radius, essentially, distance between the two charges. Okay. All right. So first, let's talk about two opposite charges, okay? And talk about bringing opposite charges together. And before we answer this question about the potential energy, what would be the sign of E if we have two charges that have opposite signs? If we have a plus charge and a minus charge. What do you think? Yeah, and what would be the sign just of that equation right there? If one of those Q's is plus and one is minus, everything else is positive. What would the overall sign be? Yeah, it would be negative. Okay. Whenever we have two opposite charges, we have a negative energy. Okay. So anytime we're talking about opposite charges, okay, we're talking about something negative. Okay. And then brought closer together. That means decreasing the value of that R. Okay? So going from, I don't know, 100 picometers to 50 picometers to 10 picometers to 5 picometers. Okay? So as that R becomes smaller, since that's on the bottom of that fraction, what does that happen? What general effect does that have when you're making a number smaller that's on the bottom of a fraction? Yeah, that makes the number larger overall. Okay, but remember it's a negative value. Okay, so let's say here the potential energy becomes more negative. Okay, it's a and that's essentially an. If we have something that's negative that becomes even more negative, okay, that's essentially exothermic. Okay. Imagine something like, I don't know, negative 10 to negative 20. Those are just made up numbers. Okay. But if something is exothermic, it gives off energy. Okay? So it's going to have even less energy than it started, and that's a little tough to think about when they're already negative. Okay? But it's going down. Okay? If we make a little scale like this, let's have negative infinity at the bottom here, then 0, then positive infinity. Okay. So anything that goes that way is going to be exothermic. I think that's a little easier way to think of it. Okay? But specifically when opposite charges are brought together, we're talking about something like that. Okay? Losing some of its own energy, okay? Giving off energy. So you can always think of magnets. Okay? Coulomb's law is essentially describing magnets to you. And when you have two opposite poles, essentially, of a magnet, you bring them together, they'll crash together. And that sound that you hear is the excess energy that it's giving off. Okay? So the energy of the magnets themselves are decreasing because they're giving off some of that energy. Okay? So you can think of that as the sound. But that works with any kind of opposite charges. Okay? Works with like an electron and a nucleus, okay? Coming closer together. Like we've talked about that before. It works with a positive ion and a negative ion, okay, coming closer together. Okay. So that releases energy. What will happen with like charges? When we have two like charges, first of all, what would the sign of E be? What would the sign of the energy be if there are two charges that have the same sign? Yeah, will be positive. Okay? So then when we have like charges that we're bringing them closer together, are we going to be making it more positive, or are we going to be bringing it down closer to 0? What do you think? What do you think? If we have, let's look at this closer. Okay? Say we've got just either two positives or two negatives. If it's two negatives, their signs will cancel. Right? If we're bringing R down, okay, if we're making R smaller because they're getting closer together, okay, if the value of R decreases, but that's on the bottom of the fraction, so what does that do overall to the energy? Yeah. Okay. So that is endothermic. Okay. It becomes more positive. See how that works? Okay. So, in fact, we can say something like this. Okay? Opposite charges, OPP, closer, something like that. Like charges potential energy increases. And you can think of that like pushing two same poles, right, two north poles of a magnet closer together. You have to push them, okay, and they kind of resist that, but you're supplying your own strength. You're supplying energy into that system to push them closer together. Okay? So that increases the potential energy of the system because you're having to expend energy to push them together. Okay? So, and I know it's a little confusing with the r on the bottom of the fraction, and we're talking about a negative value becoming more negative versus a positive value becoming even more positive. Okay? But anytime opposite charges are brought closer, that's exothermic. Okay? That gives off energy like magnets crashing together. Okay? Anytime like charges are brought closer, the potential energy becomes more positive. That's endothermic. Okay? We have to put energy into the system in order to force them together. Okay? And it requires more and more and more energy the closer we want to try to push them together. Okay? Now, we all know, right, that opposite charges attract and like charges repel, but you should be able to explain that in terms now of an energy change, okay, using Coulomb's law. Okay? So the r just has to do with that distance, and we're talking about a change in distance too, so we can talk about whether that's endothermic or exothermic. Q's, we talked about the sign of those charges, their magnitudes are also important there too, as we'll see in just a little bit. Okay? So